What specific problem does your proposed method aim to solve with the creation of narrow AI systems, particularly in the context of current general models?
The proposed method aims to address the inefficiencies and safety risks associated with current general AI models by creating narrow AI systems that are specialized for specific tasks. The research highlights that general models, while versatile, often contain a vast amount of irrelevant knowledge that is unnecessary for particular applications, such as coding assistance. By investigating the training dynamics of neural networks on a narrow data distribution and exploring pruning techniques, the work seeks to develop smaller, more efficient networks that retain essential skills while minimizing dangerous capabilities. Additionally, the study emphasizes the challenge of nonlocality in network representations, which complicates the pruning process, and proposes regularization methods to facilitate the creation of these narrow systems. Ultimately, the goal is to enhance the performance and safety of AI applications by leveraging specialized models that can operate effectively within defined domains.
How does the proposed method or algorithm work? Please illustrate this step by step, including details of the pruning and regularization techniques used.
The proposed method for creating narrow AI systems involves a combination of pruning and regularization techniques to optimize neural networks for specific tasks. First, the algorithm identifies prunable components of the model, denoted as groups, G, and computes an ablation score, S_G, for each group, which measures the change in expected loss after pruning that group. The groups are then sorted by their ablation scores, and pruning is performed greedily, starting with the least impactful components to achieve the desired sparsity. To enhance the model's prunability, a group lasso regularization penalty is applied during training, which incentivizes the network to become sparser at the group level, effectively cleaning up circuitry not relevant to the target task. After pruning, additional training on the narrow task is conducted to recover any lost performance, ensuring that the network retains its ability to perform well on the specified subtasks while unlearning others.
Can you provide a simple example demonstrating the inner workings of your proposed algorithm, particularly the CMSP task, and its implications for learning dynamics?
In the compositional multitask sparse parity, CMSP task, we extend the multitask sparse parity problem by allowing multiple control bits to be on simultaneously, which requires the network to compute the parity of bits from multiple disjoint subtasks. For example, if we have 3 control bits and both the first and second bits are on, the network must compute the parity of the bits indexed by the first and second subtasks combined. Our experiments show that when training on a dataset that includes both atomic, single control bit on and composite, multiple control bits on samples, networks learn atomic tasks more efficiently first, which then aids in learning composite tasks. This hierarchical learning effect indicates that training on a broader distribution of tasks enhances the network's ability to learn complex subtasks, as it allows the network to build foundational knowledge before tackling more complex combinations. Thus, the CMSP task illustrates that effective learning dynamics can be achieved through structured training that emphasizes simpler tasks before progressing to more complex ones, highlighting the importance of curriculum learning in neural network training.
What are the theoretical and practical benefits of your method over traditional techniques, especially concerning efficiency and accuracy in narrow tasks?
The theoretical benefits of our method, particularly in pruning and regularization, lie in its ability to effectively unlearn specific tasks while preserving performance on others, which is crucial for creating narrow AI systems. Practically, we demonstrate that aggressive pruning combined with group lasso regularization allows for a more efficient reduction in model size without significant loss in accuracy, outperforming traditional techniques like distillation and training from scratch. Our empirical findings indicate that pruning methods can consistently achieve high accuracy thresholds with fewer neurons, making them more efficient in terms of resource utilization. Additionally, we observe that pruning can be more effective than distillation, especially when leveraging existing general models, as it allows for quicker adaptation to narrow tasks. Overall, our approach not only enhances efficiency by reducing model complexity, but also maintains or improves accuracy in specialized applications, addressing the limitations of traditional methods.
How did you validate your method? Please discuss the experimental design, datasets, and performance metrics that were used to test its effectiveness.
To validate our method, we conducted experiments using a synthetic task called compositional multitask sparse parity, CMSP, and applied it to various datasets, including MNIST and language models, LLMs. For the CMSP task, we trained neural networks on both atomic and composite samples to observe curriculum learning effects, measuring convergence rates and performance on subtasks. In the MNIST experiments, we focused on a narrow subtask of recognizing even digits, comparing the performance of models trained from scratch, distilled models, and those created through pruning with group lasso regularization. Performance metrics included accuracy thresholds, specifically aiming for at least 97% accuracy, and we plotted neuron count against data points to evaluate the efficiency of each method. Additionally, we assessed the effectiveness of pruning by analyzing loss curves and recovery training outcomes, confirming that pruning methods consistently outperformed distillation and training from scratch in terms of resource efficiency and performance retention.
What limitations or drawbacks did you encounter with your method, and how could they impact the applicability of your findings?
One significant limitation encountered in our method is the non-locality of network representations, which complicates the pruning process. This means that the circuitry for different subtasks is often entangled across various neurons, making it challenging to prune specific components without affecting others. As a result, while we can achieve some level of unlearning and sparsity, the degree of entanglement is highly seed-dependent, leading to inconsistent outcomes across different runs. Additionally, our findings on the necessity of broad training distributions for efficient learning of certain subtasks may not generalize well to real-world applications, where specialized models can often be trained effectively on narrower datasets. These limitations could restrict the broader applicability of our findings, particularly in domains where task structures are less hierarchical or where data availability is limited.